Let us consider some problems on Coulomb's law. Initially, first example, the electrostatic force on a small sphere of charge 0.4 microcoulomb due to another small sphere of charge minus 0.8 microcoulomb in air is 0.2 Newton. What is the distance between the two spheres? Part B, what is the force on the minus 0.8 microcoulomb due to 0.4 microcoulomb? That is, you have to find out what is the force on the first charge due to the second charge. To solve this, first I'm considering the part A problem where value of Q1 is 0.4 microcoulomb, which can be written as 4.4 10 to the power of minus 6 coulomb, and Q2 is given as minus 0.8 microcoulomb, which you can even write it as minus 0.8 10 to the power of minus 6 coulomb, and it is said force between the two charges is 0.2 Newton. To solve this, you have to find out what is the distance between the two spheres. So what I'll do is I'll first use Coulomb's law, and from Coulomb's law I can write this expression which says F is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R squared, where Q1 Q2 as well as F is been given. So I'm shifting R squared on the left hand side and taking F on the right hand side. So the expression can now be written as R squared is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon F, or R squared is equal to 9 10 to the power of 9, which is a value of 1 upon 4 pi epsilon naught Q1, which is given as 0.4 10 to the power of minus 6 into 0.8 10 to the power of minus 6 divided by force, which is 0.2 Newton. So on simplifying, you will get an answer which is 144 10 to the power of minus 4, or take root on both sides. So by taking square root of 4 on both sides, we get an answer which is 12 into 10 to the power of minus 2 meters, which happens to be the answer that we are supposed to find out. Moving to the second part of the problem. Now into the second part of the problem, we have been asked to find what is the force on minus 0.8 microcoulomb sphere due to 0.4 microcoulomb. Now it is known F12, which is the force acting on the first sphere due to the second, is given as 1 upon 4 pi epsilon naught Q1 Q2 by R square, and F21, which is force on the second sphere due to the first, is 1 upon 4 pi epsilon naught Q2 Q1 upon R square. It is known that F12 is equal to F21, that is, the force is the same on each other. Hence you can say the force on minus 0.8 microcoulomb sphere due to 0.4 microcoulomb sphere is 0.2 Newton. Next example, 4-point charges QA equal to 2 microcoulomb, QB equal to minus 5 microcoulomb, QC equal to 2 microcoulomb, and QD equal to minus 5 microcoulomb are placed at the corners of a square ABCD of side 10 centimeters. What is the force on a charge of 1 microcoulomb placed at the center of the square? So to begin with this, I'm going to first consider a square of ABCD of side 10 centimeters. So let us say I've got a square ABCD where charges on each corner is given as QA, which is the charge on A is given as 2 microcoulomb and is 2 10 to the power of minus 6 coulomb. Charge on B is minus 5 microcoulomb, so you can consider it as minus 5 10 to the power of minus 6. Charge on C is 2 microcoulomb and charge on D is minus 5 microcoulomb. So we have located all the charges at the respective corners, and now if I consider the distances between each charge, the distance between each charge is 10 centimeters as the place at the corners of a square. Therefore, RAB is equal to RBC is equal to RCD is equal to RAD, where all put together can be taken equal to R, which is equal to 10 centimeters. Please convert it into SI units to write it as 0.1 meter. Now, with this given data, we'll first try to find the center of the square. To find the center of the square, I'm going to draw diagonals from each corners. So a diagonal from B to D and another diagonal from A to C. We see that both the diagonals meet at a certain point, where that point can be called as the center. So the center of the square is nothing but the point of intersection of the diagonals. Let us represent this point of intersection as O, where we have ROA is equal to ROB is equal to ROC is equal to ROD. All the distances should be same from the center. And now a charge of 1 microcoulomb is placed at the center of the square. So you are now supposed to find out what will be the force on the charge at the center due to A, then find what is the force on the charge at the center due to B, then find what is the force on the charge at the center due to C, and the same with respect to D. So first we'll find out force on Q naught due to QA. I write my expression in terms of Coulomb's law, which is given as 1 upon 4 pi epsilon naught QA into Q naught upon ROA squared. And we find out that this force is along the line OC. Since it is a positive charge, the electric field, or you can say the force, should be a repulsive force, which should be along OC. Next, let us find what should be the force on Q naught due to the charge at point C, or charge QC. It is known that force due to the charge at point C is 1 upon 4 pi epsilon naught QC into Q naught upon ROC squared, where we find out that this force in the direction of OA. So I can directly jump to a conclusion saying that charge on A as well as charge on B is same, as well as their distances are also same. That is, distance from O to A and distance from O to C is same. Therefore, the force due to A and the force due to C should be same. And since both these forces are in opposite directions, we can say the net force acting on the charge at the center due to the charge at A and due to the charge at C is 0. Coming to the part, let us now say force on the charge which is at the center due to the charge at B can now be written as 1 upon 4 pi epsilon naught QB into Q naught upon ROB squared, where ROB represents the distance between charge at point B and charge at the center. And we find out that this force is along OB. Because it is a negative charge, the electric field line should be inverse, or you can say there is an attractive force between both the charges. Since there is an attractive force between both the charges, the direction of force is along OB. Similarly, the force on the charge at the center due to the charge at point D should give you FD is equal to 1 upon 4 pi epsilon naught QD into Q naught upon the distance between point O and D, the whole square. And we find out that the force on the charge at the center due to the charge at point D is along OD. Again, a negative charge, there should be an attractive force between the charge at the center as well as the charge at point D, and this force results along OD. Again, it is known that charge at point B and the charge at point D are both equal to each other in magnitude, and also the distances between the center to point B as well as from the center to the point B is also same. Hence, we can say that the force on the charge at the center due to B and the force on the charge at the center due to D should be the same. Hence, we can say that the directions of these forces are in opposite directions, and the net force on the charge at the center results to be 0. Hence, we come to a conclusion saying that the net force acting on the center is due to all the forces is 0. Hence, the net force due to all the forces on it is 0.